So I'm Chiara Mingarelli, and I work on low frequency gravitational waves. I'm an ARS at CCA and also assistant professor of physics at the University of Connecticut. So I work on nanograv and pulsar timing array experiments in general. And this is an experiment which is looking for primarily the stochastic gravitational wave background that comes from the cosmic merger history of supermassive black hole binary systems. And we've had a really exciting result where these are the timing residuals of the pulsars that we used in the 12.5-year data. And if there was no signal in our pulsars while looking for the gravitational wave background, this would just kind of look flat. The expert is having problems with the pointer. Imagine this is flat, right? It would just be straight. Oh, wait, that's because this wasn't flat. But you can clearly see a departure from flatness. So what does that mean? It means that there's a signal that's manifesting at very low frequencies. Now, have we detected the stochastic gravitational wave background? No, we have not, no matter how many hundreds of papers claim that we have. We are not making that claim. What we claim is that there's some sort of common signal in all of the pulsars in the 12.5-year data. And the amplitude of this red noise is a few times 10 to the minus 15, which is what we would expect from a stochastic background from supermassive black holes. We are missing another component in order to be able to claim a detection, and that's an additional spatial correlation which appears in the pulsars that's predicted by general relativity. That has not appeared yet. So right now we have the first of two signals that we need to detect in order to claim that there's a detection of the background. Now, supermassive black holes are not the only thing that can generate a stochastic background. There could also be cosmic strings, which would have a spectral index kind of over here, and then also gravitational waves from inflation. So those things could also source nanohertz gravitational waves in the pulsar timing array band. Right now, supermassive black holes are considered to be the primary candidate, but you could also have other exotic things happening in the nanohertz band. So really all you need to know is that there's a signal, that's why that's there. There's no signal, then this is flat. So we're getting close to making a detection. So why do you care? Well, the amplitude of the gravitational wave background can actually tell you about the underlying supermassive black hole binary population. And so my student captured here, Andrew Casey Clyde, and what we did is that we took this model of the gravitational wave background where you have some sort of amplitude of the background reported at a reference frequency of 1 over a year. This is how you define the characteristic strain. And we took that amplitude and we decomposed it into these underlying parameters that are used to generate models of the gravitational wave background. So here we have black hole mass, and then this is Z max. You heard it, it's Z, I'm Canadian. That's the volume that encloses the gravitational wave background. And then this is the number density of supermassive black hole binary systems. So what's important about this kind of decomposition is that this number density of supermassive black holes tells you about the entire population. It doesn't only tell you about the black holes that are contributing to the background, but it also tells you which ones might be near enough, how many there are as a function of redshift, so that you can not only predict the amplitude of the gravitational wave background, but the time to detection of individual sources. So what Andrew found is that for this signal that's in the nanograv 12.5-year data of about 2 times 10 to the minus 15, that the number density of sources is about 6.6 times 10 to the minus 6 black hole binaries per megaparsec cubed. And that number is 5 times larger than what was previously expected. So either there's a lot more black hole binary systems that are contributing to the gravitational wave background, or there's another signal that's sourcing the gravitational wave background in addition to supermassive black holes. So that's kind of cool. And then after we detect the gravitational wave background, we're going to be really interested in finding the individual supermassive black hole binary systems. And so this is a project that I worked on with Chung Shin, who's now a graduate student at Columbia. And what we found was really interesting on a lot of different fronts. First of all, we should have around 10 supermassive black hole binaries by the end of the decade, if our simulations are right. And secondly, even if we have a gravitational wave background that's unsubtracted from the data, it doesn't impede our ability to detect the individual sources because the background is at such a low gravitational wave frequency. And so those two things do not cancel each other out at all. They don't impede detection. So even though I believe we will eventually want to subtract at least the isotropic component of the gravitational wave background to look for anisotropy, for example, even if we left it in, it's not going to impede our ability to make a detection of these continuous individual waves. So here, for example, is our prediction for what SK would look like in the presence of an unsubtracted gravitational wave background. And then the bottom one is if you manage to subtract the background. So all of these curves are what you get when you add pulsars with really short time spans. And this is important to note because the typical lore in pulsar timing is that you need very long time spans for your pulsars to be useful. But what we found is that if you're looking for the individual supermassive black hole binary systems, that even if you only have 3-year baselines, this really helps you to detect the individual supermassive black hole binary systems because their periods are also of order years. So those are our main results, and I'll leave it there.
Thank you so much, Yara. Questions, please?
I don't want to put you on the spot, but how open are you to this being the background being something else, and do you really, what would you think it might actually be?
Well, I am convinced that it's at least supermassive black hole binaries. What it could also be is, say that you had a primordial background with a blue tensor index, something sourced by an ecpyrotic theory where you have expanding and collapsing universes that would generate such a gravitational wave background. Cosmic strings could also be a thing for real, and they might also be generating gravitational waves in the nanohertz band. Or it could just be that nature really loves supermassive black hole binary systems and there's no final parsec problem. And what's even better is that they're all merging relatively, well. They're not getting stalled anywhere. Everything is going really great. And maybe that's the answer.
Yes.
Will you distinguish among those possibilities if the background does become a detected background?
Yeah, so Mordecai said, how do we distinguish between the different sources of gravitational waves once you detect the background? So the answer is in the spectral index that we expect to find. Supermassive black holes have this parameter gamma of 4.33, and cosmic strings are over here, and primordial gravitational waves are over here. But there's a lot of work to be done. So right now, everything kind of looks the same. All of these numbers are really close to about 4 in terms of the parameter space. So you have to really be able to nail down what the power law is, if it's even a power law, and characterize that before we can say what's sourcing the background. And that also speaks to Ari's point.
Okay, if there are no more questions, let me check some. Yeah, let's thank Yara again. And our next speaker is Jennifer Mead. Oh, sorry. Jennifer.
All right. Hi, everyone. My name is Jennifer Mead. I'm a second-year graduate student at Columbia University. I have recently started a new project with Melissa Ness on trying to statistically quantify the chemical scatter of metal poor stars in both local group dwarf galaxies and in the Milky Way stellar halo. Part of the reason that we are interested in these metal poor stars, particularly in dwarf galaxies, is because we suspect that dwarf galaxies should preserve the signatures of population 3 stars and really the first few generations of stars. And so suffice to say that when we look at these dwarf galaxies, we observe a chemical abundance scatter. And so in order to understand the origins of this scatter, we need to be able to model individual stellar histories and detailed chemical evolution. with cosmological simulations. But we're able to do this now. So for anyone who knows about my research with Greg Bryan and Mordecai Macklow, this is exactly what we're trying to do. But in order to understand the results of these simulations, we need to compare them to observations for which we have statistical analyses of these metal poor stars in dwarf galaxies and the Milky Way's halo. And so what we have done so far is we have taken the apogee DR16 data, and we've made two cuts, which you can see here. The halo cut for our halo stars, and then a metallicity cut for our metal poor stars. And then on the right, you can see just in cylindrical coordinates where the stars of this sample lie. We've also taken metal poor stars from the Kirby et al. 2018 data set, which gives us a sample of metal poor stars in local group dwarf galaxies. And we've done two things with this. So first, we have calculated the intrinsic scatter, which essentially just gives you the true scatter of your dwarfs, removing kind of measurement error. And we've done this for two different breakdowns of the Milky Way halo. So we've done it for the prograde and the retrograde halo, which is kind of one thing, and then the inner and outer halo. But really what you want to focus on are the green diamonds, which are the local group dwarf galaxy stars. And so the plot in the top left is a plot where all of these stars are kind of lumped together. And really the salient point here is that the local group intrinsic scatter looks nothing like the Milky Way's halo. And so you might say, okay, maybe this is because the distribution of metallicities of our stars is slightly different. But if you actually break this down into metallicity bins, which we show on the bottom right, you see that this problem in some cases is actually quite exacerbated. And we don't really solve this by breaking this down into metallicity bins. And so there's something else going on here. These local group dwarfs are not explaining the Milky Way halo. One other statistic that we have looked at so far is the Pearson correlation coefficient. And so again, on the left, we have all of the stars from the local group dwarfs thrown together. And we see something actually very nice, which is one, that all of our alpha elements are positively correlated with each other. All of our iron elements are positively correlated with each other. And for the most part, all of our alpha elements are anti-correlated with our iron elements. With the exception, though, of cobalt, which you'll see is positively correlated, but in fact, that might be actually expected because at low metallicities, we actually expect that cobalt is mainly formed in hypernovae. And so this should actually track with our alpha elements if this is true. So we have a very nice pattern, kind of expected pattern in our local group dwarfs. But if you look at the apogee data, you actually see that that pattern is just not there. Everything is positively correlated with everything else. So that's great. But if we then go and do the same thing and break this down by metallicity bins, we see that we lose that very nice pattern that we had in the local group dwarf galaxies. So we do see some negative correlations, but there's no real clear thing that's going on. And you could do the same thing for the apogee data. And again, we don't reproduce this correlation that we see between elements from the Kirby data in the apogee data. So right now, this is just a lot of questions that I'm bringing up, but we can pretty much say that the dwarf galaxies, as they are in the local group, do not explain the composition of the Milky Way halo by themselves. But we kind of know that this is already true. We know that there have been some major mergers in the Milky Way halo's past, like Gaia Enceladus or Gaia Sausage, however you want to refer to it. And so one of the next steps that we will be taking is actually to remove these known large structures from our halo data and see if the remaining stars are able to then replicate the patterns that we see in the local group dwarfs. So that is where we are right now, and I will take questions. Thank you.
Thank you very much, Jennifer. There are questions. Catherine.
The major merger of Gaia Enceladus, I mean, rather than removing it, could you just identify it and see if it explains it, or the other way around? I mean, I guess that's the same thing that you're doing.
I mean, so we can do two things, right? We can look at Gaia Enceladus separately, right? So maybe not like remove it, but bin it as we have kind of done that with this. So take Gaia Enceladus and whatever energy angular momentum space it's in, look at what kind of pattern it produces, look at what kind of pattern the other stars produce, and see if, again, that's able to replicate what we see in the dwarf galaxies.
Oh, let's see. Okay, Catherine again.
And the other point is to think about, and this is a discussion that's been going on for a while, is that the dwarfs we see today, and I think you're doing this with the metallistic hat, the dwarfs we see today are not like the dwarfs that made the halo because they're the dwarfs today. So, so I think it would be interesting to discuss how to address that issue and try and compare apples to apples. So,
yeah. So, I mean, obviously, the assumption we're going off of right now is that these dwarfs are quenched and they should not have changed too much from when, you know, there should be no ongoing star formation. Obviously, that's not necessarily true. And so, yes, that will be something that we will look at.
Okay, if there are no more questions, let's thank Jennifer again. And then our next speaker is Massimo Capasso. Yeah, Massimo, the floor is yours.
Ruiz. Okay. All right, so my name is Massimo Capasso, and I'm a postdoc at Barnard College with Professor Mukherjee. And I'm an experimentalist and a gamma ray astronomer. So my main interest is gamma ray astronomy with ground-based telescopes. So what I'm gonna quickly show you in the next slides is what I'm mainly working on at this moment, which is the next generation experiment for very high energy gamma rays, which is the Cherenkov telescope array. So what we do with current generation, and also we're gonna do with next generation experiment like CTA, is detect gamma rays indirectly on the ground through the Cherenkov light that is emitted in a gamma ray-induced electromagnetic showers. And so typically you need huge optical reflectors and nanosecond fast electronics to catch it, because it's a very fast pulse of light. What is the Cherenkov telescope array going to do better, actually bigger than the current generation experiments, is like have deployed 2 arrays, one in the northern and one in the southern hemisphere, to have a full sky coverage, and also employ telescopes of different sizes to expand dramatically the energy coverage that gamma rays telescopes typically have nowadays. So the current arrays, which are MAGIC, S, and Veritas, have 4 to 5 telescopes, actually 2 to 5 telescopes, and they cover from hundreds of GeV to tens of TeV. The Cherenkov telescope array in its full configuration is gonna expand this range, like from tens of GeV to roughly 300 TeV, and also enhance the sensitivity of a factor of 10 in the workhorse part of the array. So the bulk of the array is composed by what you see here circled. So it's the so-called medium-sized telescopes. So we have SSTs for the highest energies, LSTs for the lowest energies, and in the bulk energy range of CTA, there are the medium-sized telescopes. And most of the telescopes of CTA consists of single reflectors, so based on a Davis-Cotton design with a focal plane instrument, which is a nanosecond fast camera. And then you see an outlier here, which is a dual mirror telescope I'm gonna mention in the next slides, the Schwarzschild telescope, in which the US is heavily involved. So just a very flashy slide of about the science that we can do with gamma rays. And it goes from like understanding the origin of cosmic rays. It's been now like 100 years that we've looked for efficient, bulk of cosmic ray accelerators. We don't have a definite answer to that, despite the fact that recent findings from the LASSO collaboration have pointed towards clear evidence of clear experimental evidence of the existence of pevatrons. Still, we don't know where efficient hadronic pevatrons are yet. So this is one of the main, science topics that CTA is going to look at, but also probing extreme environments like black holes and neutron stars, or also exotic physics like dark matter, ALP, and so on. How does the SCT, so the Schwarzschild telescope, fit in all this? So one might even ask, you already have telescopes of 3 different sizes. Why do you want to have even a fourth type, which has a dual mirror technology in it? And this really constitutes a breakthrough for the technology of ground-based gamma ray astronomy, because thanks to this dual mirror structure, one is able to focus the light on a much smaller surface. That means you can use a much more finely pixelated camera, which consists of cutting-edge sensors, silicon photomultipliers, and you can have the highest image resolution ever for this kind of telescope. So just to give you an idea why we do this, on the left side, there is an image of a gamma ray induced shower as seen by a standard single mirror telescope. And right on the right here, there is how the Schwarzschild MST sees it. And the same thing goes for a proton induced shower. If you compare left the performance of a standard MST and right the performance of a dual mirror medium-sized telescope. So the US has been leading an international effort to build the SCT, and now we have a working prototype at Fred Lawrence Whipple Observatory in Arizona. And at the moment we only have the central sector of the camera equipped, which is you see an image of a gamma ray induced shower here, and this is how the central sector looks like. It's roughly 1600 channels for a field of view of 2.5-ish degrees, and we are currently building the rest of the telescope, the rest of the camera, so to upgrade the instrument. And we're gonna go from the 1600 channels to more than 11,000, and to achieve the full potential of the SCT. So one of the milestones of the project was obviously the detection of the Crab Nebula, which is the standard reference source in gamma ray astronomy. If you are honest and compare it to what Whipple did 30 years ago, this is not such a discovery, obviously not that interesting scientifically, but it was very important as a milestone because it proved the concept of a dual mirror coupled with silicon photomultiplier technology, which is non-trivial. And also, we are improving our electronics performance. For those of you who have a bit of knowledge of silicon photomultipliers, we are moving from the current situation where you basically are dominated by electronic noise and you lose the power of single photon discrimination with this kind of sensors, which is all the point why you do it. And we are improving our electronics and sensor technology so that you achieve the full potential of the instrument. And here I'll leave you with some conclusions. So the Cherenkov telescope array is going to provide unprecedented sensitivity over a much wider energy range than the current instruments. And so it's going to be a key instrument for gamma ray astronomy to complement the efforts of currently operating facilities like LASO, for example, or planned facilities like SWGO. And the US is heavily involved in CTA, and in particular with the construction of the SCT, which we are looking into upgrading in the immediate future. Thank you.
Thank you very much, Massimo. Questions? Yes, please.
Hi, this is super exciting, of course. I didn't realize the ACT was going to go down so low in energy. I mean, low to 20 GeV. What's the? Go ahead.
20 GeV is more the range of the LSC.
Oh, okay.
The LSC is the one with the larger reflective surface, and it's meant to address the lower energy. The threshold of the SCT will be higher.
And so for the 20, 50 GeV range, what kind of resolution or positional accuracy do you get? Is it comparable to Fermi, or is it still better?
Well, I think it should be somewhat comparable to what we have now. So like in the order of 0.1 degree, a bit better. So it's going to be better than existing instrument. But the main idea of the LSTs is basically rapid follow-ups of transient events. Like for example, it proved essential for magic detection of the gravitational waves event, and also the follow-up of the afterglow. So
Okay, there are more questions? Yes, please.
Would you mind using your seat mic for the people on Zoom?
Okay, yeah, the question was if I have an estimate of the size of the telescope. Yeah, okay. The SSTs, the order of magnitude is roughly 3 to 4 meters in diameter. The MSTs are comparable to what we have now. So for example, the SET has a primary of about 9.8-ish meters, like 10 meters, let's say, and the secondary is half the size. And then the LST are a bit bigger, like in the 20-meter diameter range. Like there is, I mean, the LSTs are comparable to the largest telescope there is now of this kind, which is the CT5 telescope in Namibia. Like I think it's still the biggest optical reflector, like the diameter equivalent to 28 meters. But the LST won't go that big because at some point it's you don't gain that much.
Okay, if there are no more questions, let's thank Massimo again. Thank you very much. And our next speaker is Lucy Liu. The floor is yours.
Hi, everyone. My name is Lucy Liu. I'm a third-year grad student at Columbia and AMNH. And as a third-year student, it's kind of weird time since most of my time have been spent at home. So I assume most people don't know who I am. So I'm just going to give a general introduction of the work I've been doing at home. So my advisors are Ruth Angus, Melissa Ness, and Catherine Johnson. And I have a lot of close collaboration with Tobias Buck, Nish Frankel, and Frederick Andrews. And like many people study the Milky Way, I have a dream. I want to rewind the Milky Way. So there's a few different ways to do it, and two major ways. One is to look at high redshift galaxies. Then you can directly look at how Milky Way-like galaxy evolve over time. And another way is to look at our own Milky Way and try to figure out what the history of that is. So I'm mostly focusing on the latter. And in order to do that, there are three major things I think are important, which is stellar ages, because that is directly related to time, and abundances, that's kind of going to chemical tagging where stars are formed, and also how stars move in the galaxy, which is radial migration. So those are the three things I'll mainly be focusing on. And I mostly look at survey data and simulation data. So here, these are looking at survey data, and what I'm trying to focus in here is try to get rotation periods, which is directly related to age for dwarf stars, and get dwarf star ages, and also study some get some giant star ages, and study some element abundant relation, how these how the relation changes with different chemical abundances. And so now I'm mainly focusing on using simulation data to look at how stars move in the galaxy. So the simulation we're mostly looking at right now is the Nihao simulation by Buck. And what we're looking at is recently, this paper just got submitted. So it will come out Sunday night, Monday morning on arXiv, about how stellar mergers can induce these turning points that we see in the metallicity relation in the solar radius. So it is mainly thought that the turning point is induced by radial migration, but from the simulation that we actually saw that these turning points, which are these change in relation of the metallicity versus age relation, can also be induced by infall satellites. And other than that, I've also started studying how stars migrate in the galaxy, if we can get where they're actually born. So yeah, so it's a lot of topic that I've been studying on. I know I'm not really explaining all the details in these plots, but if you're interested in stellar ages, abundances, radial migration, happy to chat.
Thank you, Lucy. There are questions from the audience. Oh, yeah. Questions? If not, I have a question. Oh, do you want to go first?
Do you explain how the infall can make that sort of turn in metallicity?
Yeah. Yeah. So what people normally thought. Anyway, below the turning point for the data, most people would think like, okay, this is how the gas naturally enrich over time. So you have older stars have lower metallicity. So as time goes to like recent time, you get enrichment over time. And above the turning point, that's what's thought to be migrated stars that are metal rich from the inner galaxy. So that's the most popular picture of this turning point. So we found that from simulation, you can get these satellite infall, which is on the order of Sagittarius. So this can definitely happen for the Milky Way if simulation does represent the galaxy. That you bring this like metal poor gas. So instead of forming stars at the metal rich end, you form star at this lower metallicity end and induce this turning point that we see in the galaxy. So that's the major idea of this paper.
Thank you. Nice work.
Yeah, very nice work. And can we, from the same plot that you were showing, can we say when that merger happened or like that interaction with the satellite happened, or that would be hard to do?
I think it is possible.
Okay.
I think one thing about this make it hard in the Milky Way is that the ages aren't that accurate. So I guess it's hard to constrain whether we can actually find the stars that are actually born from the merger.
Got it. Thank you very much, Lucy. And our last speaker of the day and of GothamFest is Katherine Johnson.
Okay, great. Let me try this before I start. Is this the button? This is the. Ah. Oh, it's up there. Okay. Okay. So, yeah, for the last few years, as you know, Gaia has revealed that the Milky Way is somewhat in disarray. So for decades, we've built careful models of the Milky Way in equilibrium because it seems pretty much in equilibrium. Gaia has shown about 10% deviations from this. This is hardly a surprise since we know the Milky Way is bombarded by satellites. Here's a beautiful illustration from Jason Hunt of what might happen to the Milky Way if it's bombarded by a satellite. So it's not exactly a surprise. And rather, it's an opportunity for us to, in some ways, study in great detail some rather fun dynamical effects. For example, some of Nico's work, since he's not talking, this is a visualization of what the dark matter halo component of a galaxy being impinged by a satellite might look like. That is going the wrong way. Is there an upside down? The bigger one. Aha. Yes, sorry. So the question is, how do we tackle this problem? Because we want to build models that are slightly out of equilibrium. And we really want to compare data sets So data science is really about feature discovery and characterization. But we really want to connect this through observations and simulations all the way back to dynamical interpretation. And our answer to this is to use basis function expansions to represent all of these. And we're really starting by just thinking about this in terms of simulations. So basis function expansions are basically representing the structure in a series of any structure, say density or any field, in terms of a smaller set of basis functions. And the idea in the end is we're going to be able to connect all of these. So that's where our name comes from, Team Beefy. But we have some vegetarians on the team, so we like to call ourselves Team Impossible Beefy, because we're also tackling something fairly hard. And we want to go on in the end to a lot of science applications. But just briefly, the other cornerstone of this is not just the basis function expansions. Conceptually, if you think about a simulation, what we're doing here is we're taking 200 million particles, and we're trying to represent the density distribution, these complex fields, by a small set of numbers, which are the expansion coefficients. That's the key to basis function expansion. What we do on top of that is we combine this with what's called multi-channel singular spectrum analysis. And that combination allows us to find both spatial and time correlations within these basis function expansions. So each of these coefficients refers to a particular shape in our feature in space, say, and you have a whole series, that's the little m. So if we make a matrix out of these series, each of these is a snapshot from the simulation. So maybe there's 100 terms in each of these, a vector, then the next vector, then the next vector. And this is for L time snapshots in the simulation. And then we lag by just one of the time snapshots and make another column and another column and another column. And what this matrix does, if you think about it, you do a principal component analysis on this matrix, and you're looking for correlations between the coefficients themselves in these vectors, but also between coefficients across time. So the principal components are representing dynamical shapes in space and time. And to give you one example, this is work that a postdoc at Columbia, Alex Johnson, has been leading. We've been looking at a really tricky case. We've been looking at an isolated simulation where the disk should be very, very close to equilibrium, so very tiny level signals. And just to give you the result, on the top, you see an m=1 spiral, 4 different snapshots. This is one of the principal components that was recovered. Here's another m= spiral, the same 4 different snapshots. You can see it has different amplitude and different phase, and these were separated by this analysis from this very quiet simulation. You can also represent this top row. Where is my pointer? You can represent the top row in terms of amplitude and phase as a function of radius versus time. So this is another representation of that same data. And here's the second row. You can see the amplitude is different and the frequency structure is different, the phase is different. And what you're seeing on the bottom is all the data from the simulation. And you can see in there, by staring at it, you could have pulled out maybe the top row, but it's very, very noisy. So the other thing that this combination of MSSA and BFE is doing for you is it's separating signal from noise. We're tremendously excited about these results as a way of pulling out dynamical signatures from simulations in an automatic way. And in the end, comparing to linear theory, they can use the same basis function expansion. We could use the same basis functioning expansion in data. But we have maybe another 5 years work to do before we get that far. But this is where we got to. Thank you.
Questions, please.
How many coefficients are you using, and is that based on how many you need to describe to some accuracy?
Exactly. So we can take, this is all based on work that Martin Weinberg's been doing for a couple of decades, 3 decades. And the idea is you can perform a fairly general basis function expansion that roughly fits the data. You can do it actually before you do the principal component analysis on time and space. You can do it in space alone, and you can actually rotate that basis function so that and add up different components so that you've got a new basis function where the smallest possible number of basis functions represents your data. So in all, we're talking about 100 to 1,000 basis function coefficients that we'd be looking at. And if you think about that, most of that would be, say, in spherical harmonics. So maybe 6 to 10 radial basis functions, and then the other 10 or more times 10, right, would come out in this spherical harmonic size. Yep. Another question?
Yes, Chris.
Hello, cool work.
Your name, I believe, is on the second page.
Yeah, two straight cameos and two straight talks. I appreciate it. So in the isolated disk case, does it ever start to develop spiral structure? And if so,
oh, sorry, said that. Does it ever what?
Does it ever develop spiral structure?
Yeah.
And if so, is that captured within the principal component analysis?
Right. So it develops this. The thing I didn't get to actually, the really cool thing here is, it was a planted question. The m=1 is it developing an m=1 spiral. What we find, I can't remember which one of these it is. This is driven by a coupling with the halo. So we can actually show that the halo also has an m=1 term, and we can show that it's the halo's m=1 term that is driving this, which is very cool. We also see in m=0, we see a very low level ringing left over from inadequacies in the initial conditions. That fades away. And we also see an m=2, and I think that's what you're talking about. The m=2 is an intrinsic mode in the disk. Maybe mode is the wrong word, but it's self-excited. So we see noise, we see phase mixing from initial conditions, we see coupling between the disk and the halo, and we actually see the disk itself self-exciting. And this is all below the 1% level in the simulation.